Any complex number a plus bi can also be represented on the complex plane as a comma b, where the horizontal axis represents real numbers and the vertical axis represents imaginary numbers. But did you know that the same number can be plotted on a plane called the polar plane? We're answering the question, what is the polar form of a complex number? And next, we'll look at how the rectangular form of a complex number can be transformed so that it can be graphed using a distance and angle measure. Let's take a look at how this works. We define the absolute value of a complex number, z, as the distance of the point from the origin. The absolute value of a complex number is the modulus, or the magnitude. As with any distance between points on the coordinate plane, we can use the distance formula to calculate the absolute value of z. Here we have 3 plus 4i on the complex plane. Our segment here is also the hypotenuse of the right triangle with legs 3 and 4. We can see that the distance absolute value z from the point to the origin is the hypotenuse of this triangle. By the Pythagorean theorem, we know that if we take each of the legs and square them, add them, and then take the square root, we'll have the length of the hypotenuse. So in this particular case, the absolute value of z turns out to be 5. Thus, the modulus of the complex number is 5. What do you notice about the modulus of 3 plus 4i? Well, it's the radius of this circle centered at the origin. That means that any complex number represented as a point on this circle has the same absolute value. Negative 3 minus 4i has the same modulus as 3 plus 4i. Next, try finding the modulus of a complex number. Complex numbers can even be represented in terms of sine and cosine using what we call polar form. Let's consider the diagram. Using trig functions, we can define a in terms of cosine and b in terms of sine. We'll do that by first creating the right triangle. A will be the leg on the horizontal, and b will be the vertical leg. Let's start with a. By definition, cosine theta equals a over r, the adjacent side over the hypotenuse. Multiplying both sides by r, we'll divide out on the right, and we'll get a equals r cosine theta. We can use a similar procedure to redefine b. By definition, sine theta equals b over r. Multiplying both sides of this equation by r gives us b equals r sine theta. Because z equals a plus bi, we can substitute in our above definitions of a and b, yielding z equals r cosine theta plus r times I sine theta. If we factor out the common factor r, we'll get r times cosine theta plus I sine theta. Sometimes we'll shorten this to z equals r cis theta. Let's look at the modulus with polar form. We can also use algebra to prove that r in polar form is the modulus of the complex number. We know that by definition, z, absolute value z that is, equals the square root of a squared plus b squared. We're going to put our right triangle back on this picture. Since we also know that a equals r cosine theta and b equals r sine theta, we can substitute these values into our equation. We can then square the quantities inside of the square root. Next, we're going to factor out r squared inside that square root. And since we know that cosine squared plus sine squared of theta equals 1, r squared times 1 is just r squared. Finally, we're going to take the square root of r squared, and that's probably the simplest step. So now we've shown that the absolute value of z, also known as the modulus, is equal to r. Let's look at another aspect of the complex number. For every complex number z equals a plus bi, there's also a complex conjugate defined as z bar equals a minus bi. For example, if we have the complex number 3 plus 4i, its conjugate will be 3 minus 4i. The complex conjugate of a pure imaginary number, such as 4i, would just be negative 4i. As we can tell from both the form of the equation and the diagram, the complex conjugate is the reflection of the original complex number across the real axis. It therefore has the same modulus, but the opposite angle of the original. Let's show that the square root of their product is equal to the modulus. We can use algebra to prove that the modulus is equal to the square root of the product of the complex conjugates. We expand the square root of z times z bar in terms of what z and z bar describe as complex numbers. Since the right side contains a difference of squares, we can distribute and simplify the multiplication, yielding square root of a squared minus b squared I squared. Since I squared is equal to negative 1, you distribute that negative 1 to the b squared, and it gives you the following. Square root of a squared plus b squared. At this point, the right side of the equation should look familiar. It's the definition of the modulus. So, we have the square root of the product of the complex conjugates is equal to the modulus. There is one key point to make here, however. We know that a real number is a complex number. However, we also know that the modulus, or absolute value of a real number, is the distance from 0. While the complex conjugate of a real number is defined to be itself, the rule shown here only applies to complex conjugate pairs, those having opposite signs of the imaginary part.
An angle in standard position whose terminal side passes through a complex number is called the argument of the complex number. The notation is argz. We can draw a right triangle of this complex number using the real and imaginary parts, where a represents the length of one leg and b represents the length of the other leg. Using this triangle, we see that tangent theta equals b over a, and we can use the inverse of tangent to solve for theta, the argument of the complex number. It's important to note that because the tangent function is periodic, there are an infinite number of angles whose terminal ray pass through a complex number. Every time we rotate 2 pi, we end up at the same location. So we'll use angles between 0 and 2 pi when stating the argument of a complex number. This example shows a complex number in the first quadrant only. What if we needed to find the arguments for complex number in the other 3 quadrants? Recall that tangent is positive in quadrants 1 and 3, but negative in quadrants 2 and 4. We'll keep this in mind as we're finding the argument of a complex number in each quadrant. Let's look at specific cases of complex numbers in every quadrant. Let's look at the complex number 3 plus 4i, which will be in the first quadrant. The real and imaginary components of this number create a right triangle. We find theta by taking the inverse tangent of 4/3. The angle is about 3/10 pi radians. Now let's think about a vector in quadrant 3 with similar components, -3 minus 4i. For complex numbers that fall in the second or third quadrant, we will use the inverse tangent and then add that angle to pi. We see that the components of the right triangle for this complex number make our inverse tangent ratio -4/-3. This is approximately 3/10 pi, so when we add pi, we get an argument of 13/10 pi. Now let's consider a complex number for quadrant 2. For complex numbers that fall in the second quadrant, we will use the inverse tangent and then add that angle to pi. We see that the components of the right angle for this complex number make our inverse tangent ratio 4/-3. This is approximately -3/10 pi, so when we add pi, we get an argument of 7/10 pi. Now let's consider a complex number for quadrant 4. For complex numbers that fall in the fourth quadrant, we will use the inverse tangent and then add that angle to 2 pi. We see that the components of the right angle for this complex number make our inverse tangent ratio -4/3. This is approximately -3/10 pi, so when we add 2 pi, we get an argument of 17/10 pi. Now you can practice finding the argument of a complex number.
We've looked at the polar form of a complex number. Now we'll look at how we can convert the rectangular form of a complex number to polar form. We'll find the modulus, which is our value of r. We'll find the argument, which is our value of theta. Then we'll use those values to write the polar form. Let's work through this example. The modulus is equal to square root of -√3 squared plus 1 squared. When you simplify that, you'll get square root of 4, which is just 2. Now let's find the argument. We have theta equals inverse tangent of 1/-√3. You may recognize this. The acute angle whose tangent is square root of 3/3 is 30 degrees or pi/6. But that angle is our reference angle because this complex number will be in quadrant 2. Subtracting pi over 6 from pi, the argument is 5 pi over 6. Now we're ready to write our complex number in polar form. Z equals 2 cosine 5 pi over 6 plus I sine 5 pi over 6. Next, try converting from rectangular to polar form. It's also possible to convert from polar to rectangular form. You must evaluate cosine theta and sine theta and simplify the expression. Let's consider an example to see how this can be done. Consider the complex number z equals 4 times cosine of pi over 3 plus I sine pi over 3. To convert z into rectangular form, we must first evaluate cosine of pi over 3. And that is equal to half. And then we're going to evaluate sine of pi over 3. And that is equal to square root of 3 over 2. Next, we need to substitute the half and the square root of 3 over 2 for cosine of pi over 3 and for sine of pi over 3. Z is equal to 4, which does not change. Cosine of pi over 3 is a half. Don't forget, we're looking at imaginary numbers, so we still have that I there. And then square root of 3 over 2. To get the rectangular form, we'll distribute. So 4 times a half, 2, and 4 times I square root of 3 over 2 is 2I square root of 3. Try converting from polar to rectangular form on your own. We're answering the question, what is the polar form of a complex number? So far, we've looked at what the polar form of a complex number is and how we can transform a complex number in rectangular form to polar form. But why do we want to have the polar form of a complex number? This polar form of a complex number can be graphed in a plane other than the complex plane. It can be graphed in the polar plane, and the modulus and the argument of a complex number are used to graph it. Next, we'll look at graphing in the polar plane. In the Cartesian coordinate plane, points are represented as x, y, where x is a measurement on the x-axis and y is a measurement on the y-axis. In the polar coordinate system, points are represented in the form r, theta, where r represents the radial distance from the pole, and theta represents the angle from the horizontal axis. Let's take a look at the following example. Let's plot the point 4, pi over 6. We can see that it has a radial distance of 4 from the origin, and its angle is counterclockwise from the x-axis and is pi over 6. To plot the point, we make a line of length 4 from the origin on the x-axis and rotate it pi over 6 degrees. We can also use negative values of r. These have the same radial distance, but their angle is plus or minus pi compared to the absolute value of r, theta. We can see this if we take a look at -4, pi over 6. To plot the point You follow the same steps we just took for 4 comma pi over 6, but then reflect the segment through the origin. So we're going to go right about here. So that's negative 4 comma pi over 6. As we can see, negative 4 comma pi over 6 has the exact same radial length as 4 comma pi over 6, but its angle is 7 pi over 6 or negative 5 pi over 6, depending on how we decide to measure it. When plotting points in the polar plane, you should observe that if you only change the value of r, the point gets closer or farther away from the pole. For example, 5 comma pi over 4 is closer to the pole than 7 comma pi over 4 because its modulus is smaller. When you only change theta, the point rotates around the pole. For example, 7 comma pi over 4 is located here, and if we change the argument to pi over 2, we're looking at 7 comma pi over 2 here. You might have also noticed that the same point can be described by many ordered pairs. For instance, 7 comma pi over 4 describes the same point as 7 comma 9 pi over 4. Because all we're doing is starting here and going an additional 2 pi. So pi over 4 plus 2 more pi is 9 pi over 4. If we rotate the other direction, we're looking at 7 comma negative 7 pi over 4. Or really any point in the form 7 comma pi over 4 plus 2 pi times n, where n is an integer. This point 7 pi over 4 represents the complex number 7 cosine pi over 4 plus I sine pi over 4. Let's show that this rectangular and polar form of a complex number represent the same number. We can think of 2 plus 2i squared to 3 as a point with the coordinates 2 comma 2 squared to 3 on the complex plane. So that's going to be about 2 comma 3.5 right there. We need to show that this is the same point we would get if we drew a segment 4 units from the origin along the x-axis and then rotated it pi over 3 radians counterclockwise. And we'll get to this right triangle right there. Using the Pythagorean theorem, we can see that the hypotenuse is in fact 4 units long. We've got a leg here that's 2 and another leg that's 2 squared to 3. Pythagorean theorem states that we square each of those, take the square root, and we'll get 4. We know that this angle, the counterclockwise one here, theta, is the inverse tangent of 2 squared to 3 over 2, or just square root of 3, since the 2's divide out here. The angle whose tangent is square root of 3 is 60 degrees, or pi over 3. So we know that this point is in fact 4 comma pi over 3. Therefore, the equivalent forms of a complex number represent the same point in the complex plane. Since these points represent the same number, we can just convert between coordinates. These formulas relate the rectangular and polar coordinates of a complex number. These come from the relationships in a right triangle. So let's go ahead and draw that right triangle. The Pythagorean theorem gives us the value of r. Taking the inverse tangent of y over x, we just need to think about the quadrant that we're in to be sure that we get the correct angle measure. To convert polar coordinates to rectangular ones, we're going to use the conversions down here. X equals r cosine theta, and y equals r sine theta. Here, the cosine is 1/2, so we multiply 4 times 1/2, and we get 2 as our x coordinate. The sine of pi over 3 is square root of 3 over 2, still the same hypotenuse, or r, is 4, and we multiply here, we will get 2 square root of 3 for our y coordinate. So we have shown that 2 is our x, 2 square root of 3 is our y. Let's look at some points that lie on the axes. For a complex number z equals a plus bi, a is the length from or along the horizontal or the real axis, and b is the length along the vertical or imaginary axis. Let's look at graphing one real number, 4, and one imaginary number, -5i. Since 4 is exclusively real, all we have to do is plot a point that is 4 units to the right of the origin on the real axis. Because this involves no rotation from the real axis, its polar coordinates are also 4, 0. Similarly, since -5i is exclusively imaginary, all we have to do is plot a point that's 5 units below the origin on the imaginary axis. This involves a counterclockwise rotation to 3 pi over 2. 1, 2, 3, 4, 5. So this point will be 5, 3 pi over 2.